The next part of circular motion has to do with vertical circular motion. So we started out by spinning something around in a perfectly horizontal circle, uh, such as somebody swinging something around the top of their head. Now let's talk about what happens when the motion goes in a vertical circular motion. So think of someone going in a loop, loop to loop, airplane making a vertical circle in the sky, uh, roller coasters, things of that nature. Uh, if we analyze the free body diagrams for all those different locations, uh, for 4 different locations on this circle, we start to see uh, some interesting things happening. So let's analyze this circle at 4 different spots. Let's analyze it at the very bottom. Let's analyze it at the very top and on the 2 sides. And let's note what's happening in this free body diagram. And we're going to neglect friction for this exercise. So on the bottom, as you've got, let's put an object on here. Let's say it's a ball. As you've got this ball here, that's going to roll around in this vertical circle. Okay. Uh, what are the forces acting on it? Well, you have the force normal from the surface of the circle, and you have the force of gravity. You have the force of gravity. Or the force weight. We also call it the force weight. At the top of the circle, we have our force normal from the surface. Remember, force normal acts perpendicular to the surface. So if you get a ball that's spinning or going in a loop, and it's at this point, the force normal is pointing downward in this case, because the surface is pushing against the ball. And force gravity or force weight is also acting downward. When we analyze this on the left and right side, you can start to see that we've got force weight acting down, and you've got force normal directed towards the center of the circle, and here as well, just opposite, mirror image of the left one. One of the things to note at the top of this circle, at this point here, is that when force normal starts to reach a point where it's equivalent to 0, this ball is going to start to leave the surface of the loop uh, and fail to make a complete loop. So often we're faced with a problem where we've got to get a minimum speed in order to have a normal force up here in order to keep ourselves in contact with the loop. And that minimum speed is going to be whenever that force normal is equivalent to 0. So if we're asked to derive an equation for that minimum speed at which the object must travel without falling at the top of the loop, we start out with the understanding of, well, that's going to happen when force normal is equal to, that's force normal equals 0. That's when, that's going to give you the minimum speed. uh, for the object to travel. Now, deriving an equation, we need to understand that we can analyze the contact here and come up with a net force. And the net force is equal to the mass times the centripetal acceleration. Well, what are the forces that make up my net force? I've got a negative force normal and a negative force weight. And my centripetal acceleration, that too is acting negatively. And we're saying that the force normal is 0 at the top for the minimum speed. So if this is 0, that cancels that out, and we're left with negative force weight, which is equal to mass times the acceleration due to gravity equals mass times centripetal acceleration. Let's bring that negative out front, and we can see that negative cancels out, and our mass also cancels out. So that minimum speed is whenever our centripetal acceleration is equal to gravity. And centripetal acceleration is equal to centripetal acceleration. We have a formula for centripetal acceleration. Recall that centripetal acceleration is equal to v squared over r. So we have a situation where now g, gravity, is equal to v squared over r. Multiply both sides by r, and you have gravity times the radius of the loop is equal to v squared, and if we took the square root of both sides, we would get our derived formula for the minimum speed. Okay, that's the minimum velocity, or minimum speed, that this object needs to travel in order to stay in contact with the loop without falling off. A couple of example problems for vertical circular motion. If we went to the old trick of swinging a pail of full water in a vertical circle, and you want to not get wet while you're spinning this pail of water in a vertical circle, if we know the radius, we want to know what the minimum tangential speed with which she swings the pail at the top. It has to be, what that speed has to be. We have derived the formula. Velocity is equal to the square root of g times r, gravity times the radius, the square root of that. If our radius is 0.8, gravity is 9.81, we take the square root. It equals 2.80 meters per second. That would be meters per second squared times a meter is a meter squared over a second squared. Square root gives us meters per second. Same type of problem with the roller coaster wants to successfully execute a 20-meter radius. What speed must each car on the roller coaster be traveling at the top of the loop? So velocity equals g times radius, and we'll get a minimum velocity equal to 14.0 meters per second. No weight restrictions due to the fact that it's not dependent upon the mass of the roller coaster or the occupants. This minimum velocity is dependent upon the gravity and the radius of the loop that it needs to complete.